Yesterday, we have stopped here, so we continue with this. A database application program running against a relational database typically runs a series of transactions. A relational algebra overview. A relational algebra is the basic set of operations for the relational model. These operations enable a user to specify basic retrieval request or a query. A result of an operation is a new relation which may have been formed from one or more input relations. This property makes the algebra or closed. All objects in the relational algebra are relations. A relational algebra overview or the algebra operations thus produce new relations. These can be further manipulated using operations of the same algebra. A sequence of relational algebra operations forms a relational algebra expression. The result of a relational algebra expression is also a relation that represents the result of a database query. Relational algebra overview. A relational algebra consists of several groups of operations. Unary relation operation, select, sigma, project, rename. So here the symbol used for project is pi, and for rename we use a row. The same way relational algebra operation from a set theory, union, intersection, difference, Cartesian product. Then binary relation operations, we use a join. Several variations of join exist. Division, additional relational operation, outer join, outer union, aggregate functions. These compute a summary of information, for example, sum, count, average, minimum, and maximum. Database state for a company. All examples discussed below refers to the company database shown here. So we have an employee here. This is a company database. Employee is a relation. So in this employee, first name, middle name, last name, SSN, social security number, birth date, address, whether male or a female, salary, super SSN, and D number. So these are the attributes which are present in the employee relation. So in the same way, department, D name, D number, manager SSN, manager start date is a department. Then department location, D number and a D location. Then project, P name, P number, P location, and D number. Works on ESSN, P project number and hours. Dependents, ESSN, dependent name, whether male or a female, birth date, and the relationship. This is what we say about a database state for the company. So along with that, we say what is SSN. SSN is a primary key, and super SSN is a foreign key, which is self-referenced. So the same employee is again referred to the same thing. So the same way, department, we have a D number. So then department location, D number, D location. Project, P number and D number. Then works on ESSN and P number. ESSN and dependent names. So these are the relations which are present in the company database. Along with that, so we can see here underlined one. So this is underlined. This is also underlined. These are the two things which are underlined. Then the project, these project number is underlined. Then works on ESSN and P number is underlined. Dependents, ESSN and dependent names are underlined. Along with that, we can see it is self-referential number, that is employee, then super SSN. So in the same way, D number, so department, D number, department location, D number and location. So then D number, so we have a department location, then project, so project number. So then works on ESSN and P number, dependents, ESSN and dependent names. So this is what is called as a database state for a company. Unary relation operation, that is select. So the select operation denoted by sigma is used to select the subset of the tuples from a relational base on the selection condition. The selection condition acts as a filter, keeps only those tuples that satisfy the qualifying condition. Tuples satisfy the conditions are selected, whereas the other tuples are discarded, filtered out. Example, select the employee tuple whose department number is 4. That is sigma, department number equal to 4 and the employee. Select the employee tuples whose salary is greater than 30,000. That is select salary greater than 30,000 and the employee. So that is what select operation. Select are A, B, C, D, then alpha 1, 7, alpha beta 5, 7, beta 12, 3, beta 23, 10. So these are the values, these are the columns, these are the tuples, these are the attributes in a relation called as a R. So the same way, now we apply a select operation, the select. So what we want to select in this, A should be equal to B and D should be greater than 5. So that is what is select operation. That is select A equal to B and D is greater than 5. So then alpha alpha, that is what alpha alpha, then 1 7, beta beta 23 10. So this is what is select, that is A is equal to B and D is greater than 5 from which relation? From relation R. So that is what a relational select operation and a select. Unary relation operation select. In general, the select operation is denoted by select. Selection condition R, where the symbol sigma is used to denote the select operator. The selection condition is a Boolean condition expression specified on the attributes of the relation R. Tuples that makes the condition true are selected, appear in the result of the operation. Tuples that makes the condition false are filtered out, discarded from the result of the operation. Unary relation operator, that is select. In general, the select operation is denoted by this sigma, and how we say selection condition, then R, where the sigma is used to denote the select operator. The selection condition is Boolean, that is conditional expression specified on the attributes of relation R. Tuples that make the condition true are selected, appear in the result of the operation. Tuples that makes the condition false are filtered out, discarded from the result of the operation. Unary relation operation, that is select. Select operation properties. The select operation, select selection name R, produces a relation S that has the same schema, same attributes as R. Select is a commutative. Select condition 1, condition 2 R, condition 2, condition 1 R. Because of the commutative property, a cascade or a sequence of select operation may be applied in any order. That is condition 1, condition 2. Either you can go for condition 1 first, then condition 2, or condition 3 for the relation R, or we can do with the condition 2, condition 3, and condition 1 and R. So that's how here we can do with the order. But it is commutative. Commutative means order is not important. Either you do this way or this way, it is fine. A cascade of select operation may be replaced by a single selection with the conjunction of all the condition. That is condition 1, 2, 3, and we can do either you can do separately, or we can use a AND operator and combine all for the relation R. The number of tuples in the select in the result of the select is less than or equal to the number of tuples in the input relation R. The following query results refers to this database state, that is employee, first name, middle name, last name, social security number, birth date, address, whether male or a female, salary, super SSN, and D number. The same way department name, department number, manager SSN, manager stat date, that is what is a department. Department location, D number and location. So that is what 1, 4, and 5. So then works on, ESSN, project number and works on, that is what is works on. Project, P number, P name, P number, P location, and D number. And dependents, ESSN, dependent name, whether male or a female, birth date, and the relationship. This is what is a company database. Unary relation operation, that is project. Project operation is denoted by pi. This operation keeps certain columns, attributes from a relation and discards the other column. Project creates a vertical partition. The list of specified column attributes is kept in each tuple. The other attribute in each tuple are discarded. Example, to list each employee's first and last name and salary of the following is used. That is project, last name, first name, and salary of the employee. That is what is a unary relation operation, that is project. Project operation, that is R. R is A, B, C, alpha 10, 1, alpha 21, beta 31, beta 40, 20. This is what is a project. So project in this 3, we want A, C. So that is A and C. Again, we can see here the 2 rows are same, that is alpha 1, that is removed alpha 1, and beta 1, beta 1, beta 2. So that is what is a projection operation. Unary relation operation, that is project. The general form of the project operation is pi, attribute list, and R. Pi is as the symbol used to represent the project operation. Attribute list is desired a list of the attributes from the relation R. The project operation removes any duplicate tuples. This is because the result of the project operation must be a set of tuples. Mathematically, set do not allow a duplicate elements. So then project operation properties, the number of tuples in the result of the operation pi, that is list and R, is always less than or equal to the number of tuples in R. If the list of attributes include a key of R, then the number of tuples in the result of projection is equal to the number of tuples in R. Project is not commutative, that is pi list 1, list 2 and R, then list 1 of R as long as list 2 contains the attributes in list 1. So the same way, examples for applying the select and project operation. So select and project, so that is D number, select people who are working for the department 4 and salary greater than 25,000, or D number equal to 5 and salary greater than 30,000 and the employee. That is what is select D number equal to 4 and salary greater than 25,000, or D number equal to 5 and salary greater than 30,000 from the employee table. In the same way, last name, first name and the salary project from the employee. In the same way, project whether male or a female and salary from the employee table. That's what the resultant of all these select and project. In relational algebra expression, we may want to apply several relational algebra operations one after the other. Either we can write the operation as a single relational algebra expression by nesting the operation, or we can apply one operation at a time and create intermediate result relation. In the later case, we must give names to the relation that holds the intermediate results. A single expression versus a sequence of relation operation. To retrieve the first name, last name, and salary of all the employee who work in the department number 5, we must apply a select and project operation. We can write a single relational algebra expression as follows, that is pi first name, last name, and salary, then department number equals to 5 from the employee, or we can explicitly show the sequence of operation giving a name to each intermediate relation. Then department number 5, from the employee we are selecting the people or employees who works for the department 5, from which table, from employee table, and store it in a department employees. In the same way, from this rows we don't want all values, we just want first name, last name, and the salary, and store it in the result. That is what is a single expression versus a sequence of relation. So then unary relation operation, the rename operator is denoted by row. In some cases, we may want to rename the attributes of relation or the relation name or both. Useful when a query requires multiple operation. Necessary in some cases. See join operation later. So unary relation operator rename, the general rename operation row can be expressed by any of the following form, that is B1, B2, etc. R changes both the relation S and the column attribute names. So like this, then row of R changes the relation name only to S, then row of B1, B2, etc. R changes the column attribute names only to B1, B2, etc. Bn. That is unary relation operator, that is rename. So in the same way, unary relation operation, that is rename. For convenience, we also use a shorthand for renaming attributes in the intermediate relation. If we write result, pi first name, last name, and salary from the department employee, the result will be having the same attributes as the department 5. If we write resultant, first name, F for first name, M for middle name, L for last name, and social security number as S, birth date, address, what is a social, whether male or a female, what is the salary of the employee, what is the super, who is the head of the department, and for which department. So that's what here, this can be renamed. So that's what here, the 10 attributes of department 5 employees are renamed. All these are renamed respectively. So the same way, examples of applying multiple operations and rename: first name, last name, and the salary. So in the same way, we take a one temporary table, that is first name, middle name, last name, then SSN, birth date, then the address, male or a female, then the salary, super SSN, and D number. So in the same way, R, that is first name, last name, and the salary. This is what is examples for the rename. Relational algebra operation from a set theory union operation, binary operation denoted by U. The result of R union S is the relation that includes all tuples that are either in R or in S or in both R and S. Duplicate tuples are eliminated. The two operand relations R and S must be type compactable or union compactable. R and S must have same number of attributes. Each pair of corresponding attributes must be a type compactable, have same or compactable domains. So the same way union operation, that is R, S. So in the R, alpha 1, alpha 2, beta 1, alpha 2, beta 3. So that is what R and S. Then R union S. So alpha 1, alpha 2, beta 1, beta 3. That is what R union S. Relational algebra operation from set theory, that is union, to retrieve the social security number of all employees who either work in the department 5, results 1 below, or directly supervise an employee who works in the department 5, results 2 below. We can use the union operation as follows. Department 5, that is select department number equal to 5 from the employee, then resultant department 5 employees pi SSN to the resultant 1. The same way, store only the head of the departments in the resultant 2. Then combine both result equals to result 1 union result 2. The union operation produces the tuples that are either in result 1 or result 2 or both. Examples of the result of the union operation, example. So result of union operation, that is result equal to result 1 union result 2. That is result 1. So this is what the result 1, then result 2 and result. So combining of these two is a result table, that is union operation. Then is relational algebra operation from set theory. The type compactable of operands is required for binary set operation union, also for intersection and set difference. R1 equals to A1 etc. AN and R2 equals to R, type compactable if they have the same number of attributes and the domain of corresponding attributes are type compactable, that is domain of A1 equal to domain of BI for I equals to 1 to N. The resulting relation for R1 union R2 also for R1 intersection R2 or R1 minus R2. So has the same attribute name as the first operand relation R1 by the convention. Intersection is denoted by this. The result of the operation R1 intersection S is the relation that includes all tuples that are in both R and S. The attribute names in the result will be the same as the attribute names in R. The two operand relations R and S must be type compactable. Then relation R and S, so this is what the intersection, set intersection operation, that is R, alpha 1, alpha 2, beta 1, that is R. Then S is alpha 2, beta 3. So then R intersection is alpha and 2. So this is what is called as an intersection. Relational algebra operation from a set theory, set difference. Set difference, also called as a minus or a except, is denoted by this. The result of R minus S is a relation that includes all tuples that are in R but not in S. The attribute names in the result will be the same as the attribute names in R. The two operand relations R and S must be type compactable. Set difference operation, that is minus R and S. So this is alpha 1, alpha 2, beta 1, alpha 2, beta 3. This is 3. R minus S, then alpha 1, beta 1. Example to illustrate the result of union, intersection and difference. So this is what student table, instructor table. Union is combine both, that is student and the instructor. So in the same way, difference, this is what the difference is. Then a student minus instructor, which are student and the instructor. So which are student minus instructor. And E, student minus instructor minus student. That's what is examples for union, intersection, and difference. In the same way, some properties of union, intersection, and difference. Notice that both union and intersection are commutative operation. That is, R union S equals to S union R, and R intersection S is equal to S intersection R. Both union and intersection can be treated as n-ary operations, applicable to any number of relation, as both are associative operation. That is, R union S union T equals to R union S union T. R intersection S intersection T equals to R intersection S intersection T. The minus operation is not commutative. That is, in general, R minus S is not equal to S minus R. Relational algebra operation from set theory, that is Cartesian product, Cartesian or a cross product operation. This operation is used to combine tuples from two relations in the combinatorial fashion, denoted by R, A1, A2, etc., AN into S, B1, B2, etc., BM. Result is a relation Q with the degree N plus M attribute. Q is a one relation where it has the attributes A1 to AN, in the same way B1 to BM. In that order, the resulting relation state has one tuple for each combination of tuples, one from R and one from S. Hence, if R has NR tuples denoted as R equal to NR and S has NS tuples, then R into S will have N Cartesian product NS tuples. The two operand do not have to be a type compactable. Cross product operation. So R, S, A, B. So that is alpha 1, beta 2, alpha 10A, beta 10A, beta 20B, gamma 10B. This is what S is. So then Cartesian product, R Cartesian product, alpha 1, take first row from S. So alpha 1, alpha 10A, alpha 1, beta 10A, alpha 1, beta 20B, alpha 1, gamma 10B. So that is what is cross product. In the same way, beta 2, alpha 10A, beta 2, beta 10A, beta 2, beta 20B, beta 2, gamma 10B. So that is what is a Cartesian product. That is what a R Cartesian product is. In the same way, relational algebra operation from set theory, a Cartesian product. Generally, cross product is not a meaningful operation, can become meaningful when followed by other operation. Example, not meaningful, that is employee, female employees are stored in female employees. Female employees, that is project, first name, last name, SSN should be present in the employee names. Then employee name into dependent, that is a employee dependent. Employee dependent will contain every combination of employee names and a dependent, whether or not they are actually related. To keep only combinations where the dependent is related to the employee, we add a select operation as follows. So example, meaningful female employees, sigma, whether select only the column as a whether male or female, from which table, from employee table. So in the same way, female employees, first name, last name and SSN from the project, and store it in employee names. Then employee names, Cartesian product dependents, that is employee and dependents. Then actual dependents, that is select SSN equals to ESSN, dependent employee dependent. Then the resultant, that is actual dependent by first name, last name, dependent name. The result will now contain the name of the female employees and their dependents. Examples of employee Cartesian product: female employees, employee names, then employee dependents, actual dependent, and result. So this is what is an example of applying a Cartesian product. Binary relation operation, that is join operation. The sequence of Cartesian product product followed by select is quite common to identify and select related tuples from two relation. A special operations called join combines this sequence into a single operation. This operation is very important for any relational database with more than one single relation, because it allows us combine relate tuples from various relations. The general form of a join operation on two relations is a1 a2 etc an, and s is b1 b2 b etc bn is r join s, where r and s can be any relation that results from a general relational algebra expression. Binary relation operation, that is join. Example, suppose that we want to retrieve the name of the manager to each department. To get the manager name, we need to combine each department tuples with the employee tuple whose SSN values matches the manager SSN value in the department tuple. We do this by using a join operation. Then department manager, that is department join manager SSN equals to SSN from the employee table. That is manager SSN equals to SSN is the join condition. Combines each department record with the employees who manages the department. The join condition can also be specified as a department dot manager SSN equals to employee dot SSN. Examples of applying a join operation, that is department manager, department name, department number, manager SSN, female, first name, middle name, last name, and SSN. The properties of join. So we have some properties when we are joining. What are the properties we have to follow? Consider the following join operation. That is, we have a relation called as R. In that we have a columns called as a A1, A2, etc. AN. And the symbol for a join, S is one more relation. By S is one more relation where B1, B2, etc. BM. Then R dot AI equals to S dot BJ. Result is the relation Q with degree n plus m attributes. Then Q is a relation where A1 to AN, B1 to BM in that order. The resulting relation state has one tuple for each combination of tuples R from R and S from S, but only if they satisfy the join condition. Hence, if R has NR tuples and S has NS tuples, then the join result will generally have less than NR Cartesian product NS tuples. Only related tuples based on the join condition will appear in the result. Some properties of join. The general case of join operation is called as a theta join, that is R join S theta. The join condition is called as a theta. Theta can be any general Boolean expression on the attributes of R and S. For example, R dot AI less than S dot BJ and R dot AK equals to S dot BI, or R dot AP less than S dot BQ. Most join conditions involve one or more equality conditions and together. For example, R dot A equals to S dot BJ and R dot AK equals to S dot BI and R dot AP equals to S dot BQ. Binary relational operation, that is equijoin. Equijoin operation, the most common use of join involves join condition with equality comparisons only. Such a join, whether the only comparison operator is used is equal, is called as an equijoin. In the result of an equijoin, we always have one or more pair of attributes whose names need not be identical, that have identical values in every tuple. The join C in the previous example was the equijoin. Natural join operation, another variations of join called as a natural join, denoted by this, was created to get rid of the second attribute in an equijoin condition, because one of the each pair of attribute with identical values is surplus. The standard definition of a natural join requires that the two join attributes or each pair of corresponding join attributes have the same name in the both relation. If this is not the case, a renaming operation is applied first. R, that is A, B, C, D, B, D, E. This is what R and this is S. R is natural join S. So then A, B, C, D, E, that is alpha 1, alpha A, alpha, alpha 1, alpha A, gamma, alpha 1, rho A. So like this we represent join. This is what is called as a natural join. So then binary relation operations, that is natural join. Example, to apply a natural join to a D number attributes of a department and department location, it is sufficient to write department location, department, Cartesian product, department location. Only attribute with the same name is a D number. An implicit join condition is created based on this attribute. Department dot D number equals to department location dot D number. Another example, Q, R, A, B, C, D, Cartesian product S, C, D, E. The implicit join condition includes each pair of attributes with the same name, that is and together. So R dot C equals to S dot C and R dot D dot S dot D. Result, keep only one attribute of each such pair, that is Q, A, B, C, D, E. This is Q is one more relation. Examples of a natural join operation. So project and the department is been joined. So we can see here a product X and project number is 1, location, and the department is 5. What is the department name? Who is a manager? What is the manager start date? The same way, project name, project number, location, department number, name, manager, SSN, manager start date. The same way, Z, project number, location, department name, manager SSN, manager start date. So that's what here we can see examples of natural join. Then computerization, reorganization, and new benefits. Department location, headquarters, administrator, research 1, 4, and 5, manager SSN, manager start date, and the location. This is what is examples of natural join operation. Complete set of relational operation. The set of operation include select, project, union, difference, rename, and Cartesian product. X is called a complete set because any other relational algebra expression can be expressed by a combination of these 5 operations. That is R intersection S equals to R union S minus R minus S union R minus S, S minus R. So then our join condition equal to sigma, a select, join condition, then a Cartesian product. Next is a division operation. The division operation is applied to 2 relations, that is R, Z, division S, Z, X, where X subset of Z, let Y equals to Z minus X, and hence Z equals to X union Y, that is, let Y be the set of attributes of R that are not attributes of S. The result of division in the relation Ty that includes a tuple T if tuples Tr appears in R with Tr Y equals to T and with Tr X equals to Ts for every tuple Ts in S. For a tuple T to appear in the resultant T of the division, the value in T must appear in R in combination with every tuple in S. That's what here the division, this is a R and S is 1, 2. So which are common in this? Alpha 1, alpha, then 2 is what? 2. So that is alpha 1, 2. So we start doing a division and the R division S is alpha beta. Examples of division, SSN phone number, Smith phone number, SSN. Then R, S, T. So that's what here example of division. The recap of relational algebra, that is select, project, theta join, equi-join, natural join, union, intersection, difference, Cartesian products, and division. So what is the purpose of using select? Select all tuples that satisfy the selection condition from the relation R, and the notation we use this one, that is select, selection condition and R. Project produces a new relation with only some of the attributes of R and removes duplicate tuples, that is pi attribute list and R. Theta join produces all combination of tuples in R1 and R2 that satisfies the join condition. That is R1 join R2. Equijoin produces all the combination of tuples from R1 and R2 that satisfy a join condition with only equality comparison. R1 join R2 or R1 join attribute 1 attribute 2 R2. Then natural join, same as equijoin, except that the join attributes of R2 are not included in the resulting relation. If the join attributes have the same name, they do not have to be specified at all. So this is what we can see. The union produces a relation that includes all the tuples in R1 or R2 or both R1 and R2 or R1 and R2 must be a union compactable. That is R1 union R2. Intersection produces a relation that includes all the tuples in both R1 and R2. R1 and R2 must be union compactable. That is R1 intersection R2. Then difference produces a relation that includes all the tuples in the R1 that are not in R2. R1 and R2 must be union compactable. That is R1 minus R2. The same way Cartesian product produces a relation that has attributes of R1 and R2 and includes as tuples all possible combination of tuples from R1 and R2. That is R1 Cartesian R2. Division produces a relation Rx that includes all tuples Tx in R1Z that appears in R1 in combination with every tuple from R to Y, where Z equals to R union Y. Then Z1 R1Z divided by division R2 Y. So this is what recap of this. I'll just stop here. One, answer your attendance.
Present, ma'am.
Abhinav.
Present, ma'am.
Aishwarya.
Present, ma'am.
Ambarish.
Yes, ma'am.
Ashok. Anu.
Present, ma'am.
Arbaz.
Present, ma'am.
Arbaz. Arjun.
Present, ma'am.
Present, ma'am.
Ashok.
Present, ma'am.
Benita.
Present, ma'am.
Bhargavi. Bhavishya.
Yes, ma'am.
Present,
ma'am. Present, ma'am.
Chaitra.
Present, ma'am.
Debmalai. Diksha.
Present, ma'am.
Deepika LG.
Present, ma'am.
Deepika MB.
Present, ma'am.
Murli Krishna.
Present, ma'am.
Gangubai. Gujiya.
Present, ma'am.
Harshit.
Present, ma'am.
Chunjar. Kavya.
Present, ma'am.
Kishore. Lata. Manisha.
Present, ma'am.
Manjunath.
Yes, ma'am.
Nayana.
Present, ma'am.
Nilanjan.
Yes, ma'am.
Nishant. Pavitra.
Present, ma'am.
Maithili.
Present, ma'am.
Priyanka.
Present, ma'am.
Pavan. Akash.
Present, ma'am.
Rajeshwari.
Present, ma'am.
Ma'am.
Rakesh. Ramya. Rashmi.
Present, ma'am.
Ravi.
Yes, ma'am.
Rizwan,
Present, ma'am.
Vishal,
Present, ma'am.
Savita,
Yes, ma'am.
Shruti, Sneha,
Yes, ma'am.
Spurti,
Present, ma'am.
Srinidhi,
Present, ma'am.
Srinivas,
Present, ma'am.
Sunil,
Present, ma'am.
Vaishnavi, Vinny,
Present, ma'am.
Ma'am, Lata, present, ma'am.
why you didn't answer Lata when I called your name? Huh?
Disconnected, ma'am.
Okay.
Ma'am, Ramya, ma'am.
Why Ramya? When I call your names, you have to answer, right? Huh?
Ma'am, Vaishnavi present, ma'am.
Yeah, marked. Yeah. We'll stop here. We'll continue in the next class.